Welcome to my channel. In our previous videos, we looked at linear dependence and linear independence of vectors. And then we also looked at in another video, we looked at spanning sets of vectors. So we use the knowledge of linear independence and the spanning set of vectors to study the basis of a vector space. So today we're looking at basis and dimension of vector space, and we use the knowledge of linear independence and the span of a vector space that we had studied in our previous videos. So the first thing I do is I define a basis of vector space, and then we try to look at several examples to ensure that the concept is clear to us. So let capital V be a vector space and S be a subset of this V. So S is a subset of V. So when do we say that S is a basis of V? We say that S is a basis of V if S is linearly independent and if S spans V. So if S meets these two conditions, that one, it's linearly, the vectors in S are linearly independent, and that S spans V, then S will be said to be a basis of V. So let's look at an example. So the first example, we have this S comprising of vectors 2, 2, and this other vector 2, negative 2. And these vectors are in R2. So we are asking the question is this S a basis of R2? So in other words, are these two vectors linearly independent? And two, do these two vectors span R2? Do they span R2? So if these two conditions are met, then we say that S is a basis of R2. So let's look at the first condition. So the first condition, we want to see whether these two vectors are linearly independent. And since there are two vectors, there are two ways of doing that. The first way, we would want to determine whether these vectors are scalar multiple. If one is a scalar multiple of the other. So if one is a scalar multiple, that is the easiest way to look at it. Or we can even look at it using this example that I used, where I try to obtain scalars A and B, such that A times the first vector plus B times the second vector gives me 0. And of course, that is the definition of linear dependence and independence. So if these two scalars exist and they are non-zero, vectors will be linearly dependent. But if they are both 0, then the vectors are linearly independent. So I just multiplied A times the first vector plus B times the second vector, and this is what I have, the system of linear equations. I reduced to echelon form, and that's what I obtained this when I reduced to echelon form. So my last row here implies that B is 0. So solving going up, if B is 0, then A is also 0. So the two scalars A and B are both 0. In other words, S is linearly independent. So it remains to show or to find out whether S spans R2. That's what I want to find out. And if it spans, since the first condition has already been met, if the second one is also met, then we say that S is a basis of R2. So let's look at the second condition. So the question is, does S span R2? And we know how to go about to tell if vectors span a vector space. So we, just as we did in our video on spanning sets, we choose a vector in R2 and we want to see whether the vectors that were given are a linear combination of this vector that we've chosen, whether a linear combination of this vector that we've chosen. So I've chosen this. It seems that I used, so I wanted to see whether this is not 0, this should be 1, 1. This should be 1, 1. This should be 1, 1. So I want to see whether this vector that I've chosen here is a linear, can be written as a linear combination of those two vectors in S. So in other words, can I obtain scalars A and B such that A times the first vector plus B times the second vector gives me 1, 1. So I just did that, and when I multiply this, I get 2A plus 2B equals to 1. And then this one will be 2A minus 2B equals to 1. I reduce this to echelon form. And when I reduce that echelon form, this is what I obtain. From here, it's clear that B is 0. So going up to the first equation, when B is 0, then A will be half. So this system has solutions. Since this system has solutions, it means that S spans R2. Remember that if it will have had no solution, then S would not be a spanning set of R2. But since it has solutions, and our solutions are here, we've obtained our solutions. A exists and B exists, such that this can be obtained. Therefore, S spans R2. Since S spans R2, and remember that S was linearly independent, it means that S is a basis of R2. Let's look at another example. Just before that example, this point that I have here is very important, that if you have a vector space, then every basis for that space has the same number of vectors. Every basis for that space has the same number of vectors. That means if you're looking at R2, then a set that will be a basis of R2 must have 2 vectors, not more than 2 vectors. Suppose I'm looking at R3, then a set that will be a basis of R3 should have 3 vectors, and not more than 3 or less than 3. So that's what I mean by this point, and we'll see how this point will work out to be very important to us. Let's look at this example. Determine whether or not each of the following form a basis of R3. So I want to see whether these vectors would form a basis of R3, whether this B will form a basis of R3, whether this C will form a basis of R3, whether this D will form a basis of R3. Now, very fast, we can disqualify some vectors here that they cannot form basis of R3 using the point that we just mentioned above, that a set that will form a basis of R3 should have 3 vectors. So that disqualifies A, because A has only 2 vectors in R3, 2 vectors in R3. So this set or these vectors cannot form a basis of R3. Look at the second one. It has 4 vectors. They cannot form a basis of R3. But these two, C and D, they can form a base of R3. So we need to find out whether they are linearly independent and whether they span R3. So that's what I've said here, that A does not form a basis of R3, since a basis of R3, and this is R3, I have not written it properly here. It's supposed to be this, supposed to be R3, must contain exactly 3 elements. But this has 2. B also does not form a basis of R3, since a basis of R3 must contain exactly 3 elements, but this has 4. So you can see what will disqualify A and B. So since C and D have 3 vectors, we need to find out whether they are linearly independent and whether they span R3 for them to form. So let's now proceed to check whether C is a basis. And see what I've stated. I've said that these are 3 vectors. So to find out whether they form a basis of R3, it's enough to determine if they are linearly independent. So once they are linearly independent, of course, they'll form a basis. They'll span. If they are linearly independent, it means they span. They'll have to span R3, and therefore they form a basis of R3. So to find out whether they are linearly independent, we seek to see whether we can find scalars x, y, z, which when multiplied by the first vector, x multiplied by the first vector, plus y multiplied by the second vector, then plus z multiplied by, this is not supposed to be equal. It's not supposed to be equal. It's supposed to be z. It's supposed to be plus z multiplied by the third vector. Plus z multiplied by the third vector. If that gives us 0, so we want to see whether these x, y, and z are all 0. If x, y, and z are all 0, then these vectors are linearly dependent. So let's just multiply very fast, because we already know how to do this. This will be x plus 2y plus 3z equals to 0, giving our first equation here. And then the second equation will be 2x plus 3y plus 5z equals to 0. And then the third equation will give us 3x plus 7y plus 6z equals to 0. So you have this system of linear equations which we reduce to echelon form, and we know how to do that, how to reduce to echelon form. So I would want a 0 in this position and a 0 in this position, and so that to achieve that, I would take row. To get my new row 2, I would take the original row 2 minus 2 row 1. And to get my new row 3, I'll take the original row 3 minus 3 row 1. So this row 1 times 2 subtracted from row 2 gives me this second row here. And row 3 minus 3 row 1 gives me this third row here. So what follows is that I want a 0 in this position. That means I would add row 2 to row 3 to get my new row 3. So my first row remains where it is, second row remains where it is. So when I add the second row to the third row, I get this third row here. What does this last row mean? This last row means that z is 0. So I solve it going up, I solve this system going up. Z is 0. So right where there's z here, write 0. That will mean that y will also be 0. Move to the first equation. Put 0 for y and 0 for z. It will mean that x will be 0. So That means that our scalars are all 0. Z is 0, Y is 0, and X is 0. And therefore, it means that the vectors, the three vectors there, are linearly independent. Since they are linearly independent, it's automatic they're also, and there are three. Remember, there are three vectors in R3. Since they are linearly independent and there are three vectors in R3, they will have to span R3. They'll have to span R3. And therefore, S, or the vector, that vector, not, was it a, no, those vectors, those three vectors would form a basis of R3. They would form a basis of R3. We did not need to determine whether they span, because we already know that these were three vectors and they were in R3, so they will automatically, since they are linearly independent, they'll automatically span. What about D? Let's try to find out whether D is a basis of R3. So just use the same reasoning. We just want to see whether the vectors in D are linearly independent. And if they are linearly independent, since they were 3 in R3, they would span. If they are linearly independent, they would span. And therefore, they would be a basis. They would form a basis. Now, so the vectors we are given were this, this, and this. So we want to obtain scalars x, y, and z. Check that x times this plus y times this plus z times this gives us 0. If x, y, and z are all 0, then the vectors will be linearly independent. So the end result will be this. The last row here means that this system has solutions, that x, y, and z exist and that they are non-zero. They exist and they are non-zero. So therefore, the given set is linearly dependent and does not form a basis of either. It's linearly dependent because you can see from this last, and if you don't you don't know how to tell that, you can look at our video on solving system of linear equations, and you can tell that this, if we have the last row here giving us 0 is equals to 0, it means that the vectors, that the scalars x, y, and z exist, and that these x, y, and z are non-zero. So let's look at another example. As I said, I give several examples so that this subject becomes clear to us. I want to use polynomials this time. So the question is, I'm given this set of polynomials. The first polynomial here, the second polynomial, and the third polynomial. Polynomials of degree 3, not degree 2. So the question is, does S form a basis of P2, the set of all polynomials of degree at most 2? So the question that, for us to answer this question, we just need to see whether this set of polynomials is linearly independent. And so to do that, we need to see whether we can find scalars x, y, and z, all of them 0, such that x times the first polynomial plus y times the second polynomial plus z times the third polynomial gives us 0. So let's just expand this. This will give us t square x, 2tx, 3x, 2t square y, 3ty, 7y, plus 3t square z, 5tz, and then 6z is equal to 0. I would collect the like terms. So those that have t square is this, and this is equals to 0. So if I put them together, I equal to 0. T square will cancel out, and I have this equation: x plus 2y plus 3z equals to 0. Then what about those that have t? I would have 2x plus 3y plus 5z equals to 0. Then what about the constants, those without a t? So again, I equate them to 0. I add and equate them to 0. So that gives me, if I was to equate the constants to 0, I would have 3x plus 7y plus 6z is equals to 0. So I have this system and I reduce it to echelon form, and my final result here, reducing to echelon form. Now, looking at this last row, it means that z is 0. Moving to the second equation here, when z is 0, y would also be 0. And then moving to this first equation, when y is 0 and z is 0, x will also be 0. So the scalars x, y, and z are all 0, which means that the vectors given to us are linearly independent, and therefore they form a basis of P2. They form a basis of P2. So I think the concept of linear of forming a basis, vectors forming a basis, is now very clear. I want to give the next example as an exercise to you. I have this example, and the question is, do these vectors, these are 4 vectors, 1, 2, 3, 4. They form a basis of R4. Of course, in R4, since there are 4, we need to test. If there would be more than 4, we would not test because they would not form a basis. Or if they were less than 4. But since there are 4, we need to test. And we need to find out whether they are linearly independent. And so just the same way, you try and do it. I did it mine here. I wanted to find scalars A, and I found that the vectors, the scalars were all 0. So try it slowly on your own time and see what I get, the same result as what I have here. So for me, the scalars A, B, C, D were all 0, and therefore the given set was linearly independent, which means it forms a basis of R4. Then I also look at an example now using matrices. The question is, do these matrices, 1, 2, 3, 4, these are 4 matrices, do they form a basis of M to 2? They form a basis. So the same thing. Want to see whether they are linearly independent. That can you obtain scalars A, B, C, D, which when you multiply by this and then add, you get a 0. Will those scalars be all 0? So let me show what I did. So I said, let me have the scalars A, B, C, D. So A times the first matrix plus B times the second matrix plus C times the third matrix plus D times the fourth matrix equals to 0. So just multiply the first element here times A, the first element here times B, the first element here times C, the first element here times D, add those first elements, equate to 0. Come to the second element here, 6 times A, negative 8 times B, negative 1 times C, 0 times D, add those results and equate to 0. Do that for this element, the element in the second row, first column. This element times 3, not times A, this element times B, this A negative 1 times C, this negative 1 times D. Add those results and equal to 0. Then come to the final element here in row 2, column 2. So 3 times A, 0 times B, 0 times C, and then 1 times D, and equal to 0. So I did that, and this is what I got. I got this system of linear equations. And I reduced this to echelon form. Reduce the system to echelon form, and this is what I got. This is what I got. My final result when I reduce to echelon form. So I go straight to the last row here and see that D will be 0. And then proceed this third last row here, and I found that again C will be 0. Then going to this, I would find that B will be 0. Then finally, going to the first row, A will be 0. So I found that A equals to B equals to C equals to D, and they are all 0. So since the scalars are all 0, it means those matrices are linearly independent, and therefore they form a basis of M22. They form a basis. So that is how we determine if vectors form a basis of a vector space. In our previous video, we looked at how to determine if vectors form a basis of a certain vector space. If a certain set, for example, a set of vectors form a basis of a vector space. So in that same video, we defined a basis and we looked at several examples. So today again, we'll now be defining a dimension of vector spaces, or dimension of a vector space, and then we'll want to look at various examples on how to determine the basis of a vector space and the dimension of a vector space. So let's first define dimension. And by dimension of vector space, we mean the number of elements in the basis of a vector space. The cardinality, the number of elements of the basis of V, that will form the dimension of V. That means if a vector space has a basis that is finite, if a vector space has a basis that is finite, then we will say that that vector space is finite dimension. That means if the dimension of the vector space is n, then the vector space will be finite dimension. So that in other words, the basis of this vector space has n elements. Now, the vector space will be said to be infinite dimensional if its basis has an infinite number of elements. So let's look at examples on how to determine the basis of a vector space. The first example here is find the basis for the vector space V that is spanned by vector R, B, and C. So there are two ways that we proceed to find the basis of a vector space. I will begin by showing the first way. And the first way, we arrange the vectors in columns and then reduce to echelon form. So my first column will be vector R, and the second column here is vector B, then the third column is vector C. So we know how to reduce this to echelon form, and I'll just remind you what we used to do to reduce to echelon form, but we already know how to do that. We already have a 0 in this position, and that is very okay. So I want a 0 in this other position. So to get a 0 in this position, I'll take row 3 minus row 1 to give my new row 3. So that's what I did. So 1 from 1, I have a 0 here, and 2 from negative 1, I have negative 3, and then negative 1 from 2, I have 3. So I have a 0 in this position and this position. So the next thing I want is a 0 in this position. So I would take row 3 plus 3 over 2 of row 2. And this will give me my new row 3. So that means the final matrix I would have, the first row remains where it is. The second row, what I did here, first of all, what I did, I divided this by 2. But it's not always, it's not a must. You can just work with what I have here. You can work with what I have here. But I divided this by 2. So you see, when we divide it by 2, what you would have, instead of the next matrix here that I would have, would be the first row remains where it is, and then the second row I divide by 2 would be 1, and then negative 1, and then this will be 0, negative 3, and 3. So this one, you see, making this one 1 makes my work easier. It makes our work easier. So let's see how that works. So let me now do this and say that now from this I come to this, and I want this to be 0. So what I did was I took row 3 plus 3 row 2 to give my new row 3. So leading ones, I have this leading one and this leading one. This leading one is in column 1, and this leading one is in column 2. You can see that column 3 has no leading one. So the leading ones are the ones that will guide me to get the basis. So I've written them that said the leading ones in each row are in column 1 and column 2. Hence, the vectors in those columns form the basis. What is the vector in column 1? The vector in column 1 was 1, 0, 1. And the vector in column 2 was 2, 2, negative 1. So that was vector A and vector B. So these two vectors, they form a basis. So this one, they form the basis. So that basis has how many elements? It has this element, vector A, and it has this other element, vector B, and those are 2 elements. And therefore, the vectors given are the basis. They form a basis of dimension 2, because we have 2 elements in the basis. We have 2 elements in the basis, so they form. So the vector A and the vector B form a basis. And so since they form a basis, this basis has only 2, and then reduce to echelon form. Let's do that and see what we get. So these are our vectors. I will just arrange the first vector in the first row, second vector in second row, third vector in third row, and I've reduced to echelon form to obtain this final matrix. And again, it's very important that I identify the leading ones. I have this leading one and this leading one. So the basis, since I had arranged my elements in rows, and this leading one is in row 1, so the vector in row 1 becomes, which was A, and also the vector in row 2, which was B. These two form a basis. These two form a basis of the vector space B. And you can still see that the dimension is 2 because that basis has 2 elements. The other way, if you arrange the vectors in rows, the other way that we would come up with a basis is that after identifying the leading ones as this one and this, and then column 1, column 2, and I've already said that the vectors in those rows, the vectors in this row form a basis. So it will be, I can take this A, vector A, and vector B to be basis, just the same way I had explained. Or alternatively, the other way I could do that, I would take this vector 1, 0, 1, and this other one 0, 1, negative 3 over 2 to form a basis. So the basis here, one can give a basis as this, or as this and this. So if I were to arrange elements in row form, there are two ways I can write the basis for this vector space. I can just take the non-zero rows. The non-zero rows become a basis, the way I've done here. This row and this row become a basis. Or I can take the original rows, the original row 1 and the original row 2 to form a basis. So we can also have the original row. Whichever way, the dimension will be the same, because if I were to choose this row and that row, then they have 2 elements. So the basis has 2 elements. And if I were to choose the original row, still the basis would have 2 elements. So I think I should look at another example to make the knowledge of basis and the dimension clear. So this is my other example. Find a basis and dimension of this set. So I'm given this set, and this set has this vector, this other vector. How many vectors are these? 1, 2, 3, 4, 5, 6. These are vectors that are in column form. Remember, they could be given to you in row form, but these ones have been given to us in column form. So I want a basis. So I would still arrange these elements the way they are in column form. The first element as the first column, the second element, second column, the third element, third column, the fourth element, fourth column, the fifth element, fifth column, and then the sixth vector here to be the column. And then reduce to echelon form. And you know how to reduce that. So when I did reduce to echelon form, what I got was this as my final matrix. Remember that these ones were arranged in column form. The vectors were arranged in column form. So we would identify the leading ones and choose the vectors in the original columns. The vectors in the original columns become the basis. So I have this leading one in first column, this leading one in second column, this leading one in third column. This fourth column has no leading one. But I have this fifth column that has a leading one. So the original vectors in those columns form the basis for this vector space. So that's what I've said, that the leading ones in each row are in columns 1, 2, 3, and 5. Thus, the vectors in column 1, original vectors, column 1 was this vector, column 2 was this, column 3 was this, and column 5 was this vector. These 1, 2, 3, 4 vectors form a basis. And since there are 4, the dimension of S is 4. The dimension of S is 4. So our set was set S, that's correct. So that set S has dimension 4. Okay, let me now look at another example here. Find the basis and dimension of this span. This span has how many vectors? 1, 2, 3, 4, 5, and 6 vectors. As I've said, we can decide to write in column form. So that's what I did. That's what I did here. This vector, I put it is it? So let me see. Find the basis and dimension of this. So which one did I arrange here? Did I arrange in column form? No. Not arrange in column form. What about? So let's just do it. Let's just do it and see. It seems this. I had already worked on it. Then what I just wrote here were the results. So let's just do it. I have 1, 0, 1, 1 as my first column. The second column will be negative 1, 1, negative 1, 0. And then this other one will be 1. With how many zeros? 1, 2, 3. 1, 2, 3. So that is the third one. 1, 2, 3. So I'm coming to the fourth one. 0, 1 with the 2 zeros. Then coming to this other one, it is 0, 0, 1, 0. So I've written this. So I'm coming to this 1, 2, 3, and then 1 here. So I reduce this to echelon form. You know that I want a 0 in this position and a 0 in this position. So what do I get? The first row, remember, it is 1, negative 1, 1 with 3 zeros. Then the second row, measure it is 0, 1, because you already have a 0 in this position. So this will be 0, and then 1 with 2 zeros here. And then I need a 0 in this position. I'll subtract row 1 from row 3. So subtracting this from that, I'll have a 0. And subtracting this from this, I'll have another 0. Subtracting this from this, I would have negative 1. Then this one remains a 0, that remains 1, that remains 0. So 0, 1, 0. Now I also want a 0 in this position. So just subtract this from that, I have a 0. Subtract this from that, I have a 1. Subtract this from this, I have negative 1. So I'm done with this. So now this is 0, this is 0, and this is 1. So 0, 0, 0, 0, 1. I'm supposed to be negative 1, 1, negative 1. This was to be 1, which is 0. This was to be 0, 1. Yeah, so the problem was only here. Now, so this is what I have. Not exactly, because I have a 0 here. So what I did was, I now have this leading one. I want a 0 here and another 0 here. So fortunately, we already have a 0 here. So we only need to create a 0 here. Okay. So let me see what I have. The first row remains where it is. The second row remains where it is. And then to get the third row remains where it is, because we already have a 0 here. So I would have a negative positive 1. So let me just write, there will be positive 1. No, negative 1, 0, negative 1, 0, 1, and that. So this is where I have a problem. I need a 0 here. So I need only to subtract this row from this row. So when you subtract this row from this row, 1 from this, it will give us 0 here. It will become a 0. Then 0 from negative 1, I will merge the negative 1. Then 1 from 0, I would have negative 1. I would have negative 1 in this position. I would have negative 1 because it was 0. It was 1 from 0. I would have negative 1. And then this was 0. This was 0. But you already know to write in echelon form. I'm just repeating what you already know. Now, so you look at this element and this. I need a leading one in this position. So I would multiply this row by negative 1. And so what do I get? Multiplied by negative 1, this would be positive 1. And this would be negative 1. And now use this one, this leading one, to create a 0 in this position. That is what gives me the final matrix, because what I wrote here was a final matrix. What I wrote here was a final matrix for reducing to echelon form. So look at the first row. It remains where it is. The second row remains where it is. The third row is 0, 0, 1, 0, negative 1. Is it supposed to be negative 1 or positive 1? Yeah, you try and go through slowly and see what you get. Now, so what about here? Make a 0 here. So just add this. We have a 0. Add this. Supposed to be negative 1, obviously. So you go through here and see what you get. I think during the calculation here, since they are squeezed, I must have missed something. But this is, let's suppose this is the final matrix that I get. Let's suppose this is the final matrix. What I'm interested in is the basis. But we'll go through slowly and see. So to get the basis, since these vectors were arranged in column form, I would choose the leading ones. You have a leading one in the first column, the leading one in the second column, the leading one in third column, then the other leading one that I have is in 1, 2, 3, 4, 5, 6th column. It's in the 6th column. So the original vectors in column 1, column 2, column 3, and column 6 form the basis. So let's see. So what did I say? What I say is that the leading ones in each row are in column 1, column 2, column 3, and column 6. Hence, the original vectors in those columns form the basis. That is, the basis will be this set. The basis will be this set. And what is the dimension? The dimension of this vector space will be the number of elements in this set. 1, 2, 3, 4. So that is dimension 4. But as I said, I really doubt this result. What I want you to do, because of time, arrange these elements in column form and reduce them to echelon, because you already know how to do that. And from there, use our knowledge of finding the basis to find the basis for this vector space. Okay, let's look at this example. Find a basis for R5 that contains these two vectors. Find a basis for R5 that contains this vector and this vector. Now we must be knowing the natural basis for R5. The natural basis for R5 is this vector, this other vector, this other vector, this other vector, and this other vector. So this is a natural basis. We have 1 with 4 zeros, then 0, 1 with 3 zeros, then 0, 0, 1 with 3 zeros, then 3 zeros, 1 with a 0, then 4 zeros with a 1. So this is a natural basis for R5. Now, what does the question want? The question wants us to find the basis for R5. And that basis must contain these two vectors. So I just added these two vectors to these other 5 vectors, 1, 2, 3, 4, 5, and formed a column matrix. So I began with the vectors that I'm being asked to. The first vector here was 1, 1, 0, 1, 0. So I put it in the first column. You can see there. Then the second vector that our basis must contain is negative 1, negative 1, 0, negative 1, 0. And so I put that in our second column. And then I put these other vectors in the other columns. This one in the third column, this in the fourth column, this in the fifth, and so on. Then reduce this matrix to echelon form. When I did that, when I reduced this matrix to echelon form, this is what I got as my final matrix. Remember that these vectors had been arranged in columns, and the leading ones are this is a leading one in column 1. The other leading one here is in column 3. So I'm taking the original vectors in those columns. This is column 2, column 3, column 4 has no leading one, column 5 has a leading one. Column 6 has a leading one. And then column 7 has a leading one. So the original vectors, this vector, this, and this, and that, they form a basis for R5. They form a basis for R5. And you can see we have answered the question. Those that we needed a basis that will contain those two vectors. So let's see what my solution was. My solution was that the vector in column 1, those vectors that I ticked, column 1, column 3, you can see it, and then this other column, where we have the leading ones, column 3, it's here, 1, 0, 0. Then the leading one in this other column, third last column, 1, 2, 3, 0, 0, 1, this. And then you have a leading one in the second last column, this vector. And then you have a leading one in the last column, this vector. These will form a basis. And how many are they? 1, 2, 3, 4, 5 elements. And so the dimension of this basis is 5. And that is how we've determined the basis of a vector space and the dimension. Remember that the dimension will be the number of elements